Diffusion of Differently Sized Silica Beads in Water by Megan Wild, Jessie Plaehn, and James Liu. So our question was, how do differently sized silica beads in water affect the rate of diffusion? Diffusion is the movement from higher concentrations to lower concentrations. If uncharged, any size molecule can diffuse through the membrane. If polar, however, it depends on size. Small molecules can diffuse through pores, but large molecules must use carriers. Diffusion is important because cells use diffusion to get nutrients into their body and then use those, and also get rid of waste.
So our hypothesis is that we believe that the smaller diameter silica beads in water will have a greater change in velocity and position over time. Therefore, it'll take longer for them to settle, and they will diffuse further than the larger diameter silica beads. In our experiment, we tracked the position, velocity, and then calculated momentum of the 3 differently sized silica beads in water, and we used the tracker software. We did 3 trials of each, finding average velocity in the X and Y direction of the 1.5, 2.5, and 5 micron silica beads. We then used the data and analyzed it to find the impact it has on diffusion. In order to find momentum, which is the quantity of motion of a moving body, we used the formula P equals mv, which is mass times velocity. We used the tracker software that gave us velocity, and then we needed to calculate the mass of each bead.
And so to find the mass of each bead, here's an example of the 1.5 micron silica beads. We took the micron, which is the diameter of each bead, and we converted that to centimeters. And so with the diameter of each bead, we can divide that by 2 to find the radius and plug that into the volume of a sphere equation, which is 4/3 pi r squared. And so for the 1.5 micron silica beads, we found the mass to be 3.18 times 10 to the negative 12th grams. And for the 2.5 micron silica beads, we found it to be 1.47 times 10 to the negative 11 grams. And for the 5 micron silica beads, we found it to be 1.18 times 10 to the negative 10 grams. And so here's our data for the 1.5 micron silica beads in water. To the left, we have a video of the beads, the particles moving. And so what we did was we found the average velocity in the X and Y directions, and we used the Pythagorean theorem to find the vector. And so by finding this vector, we plugged it into the P equals mv, the momentum theorem. And so we found the momentum of the 1.5 micron silica beads to be 2.4 times 10 to the negative 11th grams times micrometers per second. And similarly, we did the same exact thing for the 2.5 micron silica beads in water, and we found the momentum for that to be 6.70 times 10 to the negative 11th grams times micrometer per second. And for the 5 micron silica beads in water, we did the exact same thing to find 3.40 times 10 to the negative 10 grams per micrometer per second. And for all these, also to add, there's a graph on the bottom that shows velocity over time.
A few of the many errors that were possible in this experiment, we included human error, like calculating the data incorrectly, using outliers of bead movements that could skew the data, and not properly tracking the beads due to blurred vision during the movement of water.
So we conclude that with the calculation of these momentums using the P equals mv formula, the larger the diameter of the particle, the longer it will take for settle, and therefore the greater rate of diffusion. And so we related to Newton's first law, which is an object in motion will stay in motion unless acted on by an opposite force, and also the conservation of momentum, which is final momentum equals initial momentum. So these laws are applied by, for example, in the computational and the experimental. In the computational, when the particles hit the box, the momentum is transferred from the particles to the box and from particle to particle. And then in our experimental, the momentum and the beads are also transferred from bead to bead and also to the water molecules. And eventually, over time, these particles will begin to slow down. Eventually, they will settle. And the reason why Newton's first law comes to play here is because the reason why these beads slow down is because they hit water molecules and they also hit one another.